Alright, welcome back to another exciting video for our class. We're going to find the derivative of sine over cosine using the quotient rule. Alright, so we have, of course you already have it memorized because you heard me sing. Alright, dy dx equals ho d high. So we have ho, the low function, d high. The derivative of sine is cosine. Okay, minus high d ho. High, the top function. Okay, sine of x. D ho minus sine of x. That's the derivative of cosine. Over ho ho. Cosine of x squared. Alright, we could do a little bit of simplification. Alright, cosine times cosine, that's simply cosine squared of x. Sine times sine, and we have plus sine squared of x all over cosine squared of x. And I'm just rewriting it, okay, with the squared in the middle there. Now, if you remember, because of course you remember all of these identities from pre-calculus, cosine squared plus sine squared, that's just 1. Okay? And then we have 1 over cosine squared of x, which, again, we can, from pre-calc, remember these identities here, I can also write that as secant squared of x. So if we look back, sine over cosine, since you remember that, that is tangent. So we just found the derivative of tangent equals secant squared of x. Now we could derive all of these other ones by using the quotient rule. Remember, secant would be 1 over cosine, cotangent, 1 over tangent, or cosine over sine. So we could do that, but we don't have to. It's right here. You just have to remember it forever. Alright, find the derivatives of each of the following. Now that we know these, we're going to remember them forever. We can find the derivatives. So for this one, we have g prime of x. Well, the derivative of x, that's just 1. Derivative of negative tangent of x would be negative secant squared of x. Alright, there is another way of rewriting that using trig identities, but we won't bother right now. If anybody knows, show me tomorrow in class. Alright, and if we want to take the derivative of this, oh wait, that's a product. Good thing we know the product rule. Okay, dy dx, the derivative. It's the first times the derivative of the second. The derivative of secant is secant x tangent x. Secant x tangent of x. Okay, so we have the first times the derivative of the second plus the second function times the derivative of the first, which is just 1. So if we wanted here, we could rewrite it without the 1, but I think that's pretty good. We have 2 more examples. The first one is going to be longer than the second one. The second one is a magic shortcut. Alright, so we have, we could break it up, right? 1 over sine minus cosine over sine, but that would turn into this. So let's just practice using the quotient rule so you can get really good at it. Alright, f prime of x equals ho d high sine of x minus, or times, what's the derivative of the top? And it looks like it's going to be sine squared of x. Alright, minus high d ho, the top function, times the derivative of the bottom function. So the derivative of sine would be cosine. All over ho ho sine squared of x. Of course we can simplify this. Alright, so we have sine squared of x. Sine squared of x minus, alright, I'm going to multiply this out first so I don't scare anybody with the steps here. Cosine, oops, I meant to write cosine x. And then we have minus cosine squared of x. All over again, sine squared of x. We we can simplify just a little bit more here, because I can distribute this negative. Alright, so if I do that, I get sine squared of x minus cosine of x plus cosine squared of x. And again, all over sine squared of x. Now we can simplify it just a tiny little bit there. Sine squared plus cosine squared, that's just 1. Alright, so we have 1 minus cosine x all over sine squared of x. And remember, if we feel like it, we could break it up, right? It could be 1 over sine squared of x minus cosine over sine squared of x. Should we keep going? Of course not. We're too lazy, right? So this could be cosecant of x. And this could be cotangent of x times cosecant of x. And we're going to see that right here with part B. Alright, the derivative of cosecant of x. If you look at the top of the paper, it says that it's negative cosecant of x times cotangent of x. Right, so negative cosecant of x times cotangent of x minus the derivative of cotangent of x. So plus cosecant squared of x. Alright, and that is actually exactly the same exact thing we got here. Okay, 1 over sine squared of x, that's the cosecant of x part. We can break this apart here. Alright, so you're going to notice sometimes you do the problems differently, but you end up getting the same answer. If you go to part A, if we broke it up first, 1 over sine of x minus cosine over sine of x, we would have gotten cosecant x minus cotangent of x. Alright, so maybe you're going to do this on a test and you forget the derivative of cosecant. Well, then it might be a good idea to go back and rewrite it this way. Then you could just use the quotient rule. Okay, so you have to be flexible. If you don't always memorize it, think of a way to find it. Alright, let's keep going. Higher order derivative. So we mentioned this. Okay, position, s of t. The derivative of that is velocity. Remember we had like miles and hours. So velocity was in miles per hour. Okay, and acceleration is just the derivative of that. It's called the second derivative of s of t. Alright, and you could read it as s double prime of t. Okay, so here's some different notation. We have y prime, y double prime, y triple prime, and then we go to y to the fourth derivative. Okay, once we get higher than 3, the tick marks start getting confusing, so we just put the numbers in parentheses. Okay, and then the same way to write it here, we have dy dx, d squared y dx squared, so we're taking the second derivative with respect to x, okay, and then third, fourth, and just take a look at that notation. Okay, so we're going to just go ahead and find the first 5 derivatives of this. Sounds like a lot of work, but we know it's not too bad because we just have polynomials there. Alright, so I'm going to write it in this notation. You can choose y prime if you want. If we take the derivative, using the power rule, we get 3x squared minus 10x plus 6, okay, and then plus 0. So there's our first derivative. Alright, now let's go to the second derivative. Just apply the power rule again. 6x minus 10. How exciting! Alright, we could keep going. D cubed y over tx cubed, the third derivative. Well, this looks tough. The only one we have left is 6. Alright, so now that we have a constant. Alright, if we take the fourth derivative, if we take the derivative of any constant, it's just 0. So if we take the derivative of 0, it's just 0. Alright, so notice each time here, the power decreased by 1. So we notice that. If we have a cubic function and we take the derivative, we get a a quadratic function. If we take the derivative of a quadratic, we get a linear, okay? And so that relationship still holds even if you're doing continuous derivatives. Alright, so only two more examples for today. Here we have a position function, and we're trying to find the acceleration. So if you know, okay, s prime of t, that's velocity. The derivative of position is velocity. Alright, so if we take the derivative using the power rule, we get negative 16, or 1.6, sorry, t. Take 1 away from the power, so we have that. And our units there are in feet per second. It's velocity. Alright, and then we need to find acceleration. Well, that's the second derivative of position, or the first derivative of velocity, right, equals acceleration. So we just have to take the derivative of that. So that would be 1.6 t to the 0. And again, our units, those are important. They'll come in handy later. Are feet per second squared. So how many times stronger is the acceleration due to gravity on Earth than it is on the moon? Well, on Earth here, oh man, I just noticed something. This says feet, this says meters. How dare I? Meters, there we go. Okay, so on Earth, we know, of course you know this because you took physics, right? Acceleration due to gravity is 9.8 meters per second squared. So how much faster is that? Well, you can figure it out and tell me. I think it's like 6 1/8 times stronger. So you tell me if I'm right tomorrow. Okay. Times stronger. Okay, so things are going to fall a lot faster on Earth than they are on the moon, and that has to do with the acceleration of gravity. Okay, one more. Bear with me for one more. Of course, we always read directions. So it says the graph below is of f prime. Okay, this one's f prime there. So let's sketch and label. Let's start with the two derivatives there. F double prime. So that's just graphing the slopes of this function. Well, right here, I have a horizontal tangent line, so my slope would be 0. And notice here, my slopes are positive, and they're increasing. My slopes are negative, okay, and decreasing. So, and if we remember, this looks like a cubic, so we could probably draw, whoa, alright, try again. Yep, that's much better. There we go. Alright, one side looks good. It's perfectly symmetrical right there. I'm sure you can see that. This would be our derivative, okay, of that first function. So if you look over here, we have the slope, okay, of this function was positive, but it's getting closer to 0. So I have my slope is positive, it's really positive, and it's getting closer and closer to 0. Same thing over here, perfectly symmetrical on that side. Alright, so our slopes are very small, but then they start getting steeper and steeper and steeper as we go up. Alright, let's try the third derivative, f triple prime. The derivative of this quadratic, well, again, we have that horizontal tangent, so it looks like it's going to be 0 here. And it is increasing, okay? Our function is increasing, our slopes are positive. Here our function's decreasing, our slopes are negative, so maybe we can have something a little more linear, okay? And this one, we would label that as f triple prime. The only new thing now, right? I gave you the graph of the derivative, but I want you to graph f. So maybe we can use this idea that it's a cubic, and we could graph a quartic function, okay, to the 4th power. Alright, so we have right here, our derivative is positive, okay? Our slopes are positive, so that means our function is increasing. Right, so maybe we could have something kind of like this. On the other side, our slopes Our slopes right here are negative, so that means our function is increasing. Oh, got a little squiggly there. Let's try again. Better. Sure. Alright, so let's double check this. If this was our graph, our function's decreasing, so our slopes are negative. Okay, we're good there. Our function's increasing, so our slopes are positive. So it looks pretty good right there. Alright, so that we're going to work on that relationship between the graph of the derivative, the graph of the function more in class. Now, did I have to draw it right there? If I drew it, if I could just draw straight, that would help. If I drew it right here, okay, would that make any difference? The horizontal or horizontal tangent line's still right there. We're still increasing, okay? We're still decreasing from on this side. So I could just subtract, say, 2 from our function and move it down, or it looks like I actually subtracted 4. So this would be like f minus 4, but it'd have the same derivative, okay? Or what if I move it up here? What if I drew it right here? It's going to be the same kind of function. Now I just added something. It looks like I did f plus 7. So we're going to learn there's a whole family of functions that have the same derivative. The only thing that's differing is a little bit of a constant right there. Alright, continue working on your problems and come into class with any questions tomorrow.